how are people's projects going? Anybody want to tell us quickly where they're at before we decide somebody to tell us quickly where they're at? Okay.
Yeah, I just started looking at the codes for servo motors and try to test it out. And because my project involves a potentiometer, a bar swipe potentiometer that can adjust the angle that the servo motor turns. I'm still testing that. So.
Okay. All right. Anybody else? Recording data. All right. From what sensors so far?
Temperature, pressure, humidity, and soil moisture.
All right. Awesome.
Could be useful to look at the schedule together for a second.
Yeah.
John, I don't know if that's easy to get. Just from the website, kind of ask ourselves the question, where do we stand right now, and looking forward to the idea that
So let me blow this up a little bit.
people are going to present some things that that could be as early as 2 weeks from now, roughly.
Well, so we're sitting right here, and then Thursday next week, this is your Thanksgiving break week. And then there's a week after that, and then it's presentations of your projects. So there's basically, what's that, 6? 1, 2, 3, 4, so 5 lecture periods after this, and then project presentations.
So beginning in December?
Yeah, it's the first week. It's the week before AGU in December. The last week that anybody in this class will be here almost, since most people are going to be at AGU.
That's the week of the 5th, so it's the 6th and the 8th of
Right.
December are those days there, actually 31, 32.
And what we're thinking there is, you'll bring your project in and explain kind of what you wrote in your proposal, what the problem is and how you solved it, and do like a little demonstration, maybe show some data that you've collected with it, or show us your thing working. And we've had these quizzes and we said, don't worry too much about their impact on your grade, because the project is half of your grade. It's the dominating factor, because that's what we really want people to get out of this, is the ability to build something. So is anybody having big stumbling blocks? I know I've talked to a few people about problems they were having. No big unresolved issues? Okay, so if you have an issue, come see us. I, as of 2 o'clock this afternoon, won't be here until Saturday night. And then Chris is gone Thursday after class and Friday. So if you don't get a hold of one of us by then, you'll have to get in touch with us next week.
Yeah, which is another way to say, anything that comes up related to your projects, or maybe even the stuff we were doing last week, just grab one of us.
Yeah.
I'm around, I should be in the lab most of tomorrow. So.
I have one question. So
Mhm.
do we need to write a report about the project, or just make some slides to present?
I think we were thinking just a presentation, right?
Yeah,
There's no real report.
Presentation will have to have something that goes along with it. So you say a report, but I suspect it'll be some slides that document what you've done, and at least a page or two that just goes along with the slides, kind of explains, so not a big paper, but think, something that you could look back on 5 years from now, or 10, and say, oh yeah, what did I do? How did I do it? So something that's written in the form that it will at least summarize what you've done, maybe some problems you ran into, some things you learned. It'll be a document that'll be useful to you.
And it's something that we have to talk about, but I think we could even pretty easily, you write it as just a plain text file, and like out here under resources or something, we could just have links to everybody's, your pictures and your text. So your project could be part of the website, because there are other people looking at the website that aren't in the class. There's lots of other people looking at the website that aren't in the class and using this material. So your project could be the thing that makes them see they can probably do it too. All right? Okay. So today is going to be Signal Integrity and Input Impedance Day, which this is a big one for anybody that records data, because signal integrity is how clean does your signal get from your transducer all the way into your recording system and saved. And input impedance is something that we've seen multiple times in the lab stop somebody's experiment in their tracks because they're trying to connect this system to this system and do some kind of joint recording, and all of a sudden everything goes completely crazy. Generally, that's some kind of impedance issue. Before we get into it, a couple notes. One, when we do stuff in the lab, like the strain gauge stuff, please make sure you pick up after yourselves. Steve will come find you because there was a lot of trash from the strain gauge stuff left around. All the parts for the projects are in. There were some things that were on back order, but they're all here now. So if you don't have everything you need, something went horribly wrong, and you should come talk to us. And batteries. Several people are using batteries, lithium-ion especially. I think we had 4 or 5 of those that were ordered. Lithium-ion batteries are dangerous. As you know from Samsung, the Note 7 debacle, where now you can't even take one on an airplane, as a demonstration of battery power unintentionally. This was a NASA JPL robot that caught on fire. So everybody, they've been working on this. This is a lithium-ion battery charging problem. They improperly charged them, which you could very easily do this to yours, and you can see the entire thing exploded. Luckily, nobody's in the lab, but that had about the same potential or the same energy as a stick of dynamite. The small batteries, like you would use on a drone or something like that, if you were to convert all of the energy in them, say you stepped on it, it could propel you about 200 meters into the air. So these things are no joke. They can burn down your house. So be careful, follow the instructions, and if you have any questions, ask one of us before you do something. Like, never short it. Make sure you're charging it properly because they can be dangerous. So any questions from anybody that's using batteries or anything like that? Also, they can provide a lot of current. I have accidentally shorted across a lead acid battery and had the wire that was taking power to my circuit vaporize and leave its burned trail in my carpet. So you want to be really careful with these things. And we're going to talk about, before we really get into the slides, we're going to talk about some tools and instruments that are in the lab that you can use when you're working on your projects that are going to be useful. Another thing that people should look at on the website up in electronics, a lot of problems that people had with building the Wheatstone Bridge or things on their projects have to do with soldering. So there's this soldering section on the website that describes all the tools, but watch these videos down here. They're, I think, about half an hour long, but if you watch those, you'll actually be able to make good solder joints, which are the key to getting your project to work well. Bad solder joints mean bad connections, mean really weird behavior from your project. So take the half hour, when you're eating lunch, watch those, and they'll save you hours and hours of time. Okay, so some test equipment. I have a selection up here. Up on top, we have a power supply. We have several of these in the lab. So let me disconnect these leads. You can turn it on. You see we can vary the voltage that it's putting out. It's kind of like a battery that we can vary voltage. And it has a current limiting adjustment. In this case, I've got it turned all the way up because these can't provide a lot of current. But if your project needs more power than your laptop USB can provide, which is not very much, like if you're running a big motor, you need to use one of these guys to power your project. And we've got 3 or 4 of these up there in the lab. So if you need some help finding one, we can help you out with that. Another common piece of test equipment, actually, let's do this first. This is probably the one that you'll use second most, is the multimeter or the volt-ohm meter. It was clear that when we were doing one of the labs in here that people may not be super familiar with how to use these. So these flukes are really easy to use. You just turn it to voltage AC or voltage DC or millivolts or ohms if you want to measure resistance. So if I touch the two, and they are sharp, if I touch the two together, you see it's 0.4 ohms, so not much resistance in the wires. Diodes, and then current measurement. So these are pretty easy to use. You just have to turn it, and then they are so-called auto-ranging meters. So they will change their measurement range to suit whatever voltage you're putting on the probes.
How did you get used to just messing with that kind of thing?
Right.
I don't know about you, but every time I look at that thing, I can never remember what the international symbol is for AC
Yeah.
And same thing with the millivolts. Okay, so you know, if you put out millivolts, and it's going to overrate if you have a 2 or 3 volt signal, or 20 volt signal, because it's meant to measure something that's less than a volt. But that's what it is. It's not going to break that thing. And it's super useful to get used to be able to grab this thing and use it to troubleshoot, figure out what's going on in the project.
Yeah, the first rule of troubleshooting is thou shalt check voltages everywhere. So if you know there's supposed to be 5 volts here, measure it. Is there 5 volts? You know, there's supposed to be 3.3 volts here, measure it. These are the two symbols that you'll see. The one with the squiggly on top is for alternating current, because an alternating current waveform will look like a sine wave. And then this is the DC symbol if you're measuring DC voltage. There are a couple meters like this up there. I personally am not a huge fan of this kind of meter, but you can see it has the voltage and the DC symbol, and then 600, 200, 20, and 2. And so those are the max voltage that it can measure on that range. So you have to, if you know you're measuring 5 volts, well, it's above 2 but below 20, so you would set it to the 20 volt range. So you have to set the range manually on these kind of meters. Otherwise, they're not going to give you either very good resolution, or they'll just probably pop one of the fuses inside. And several of these have this little transistor tester. Just don't use it. They're never, ever right. Okay, another piece of test equipment that we've got is a function generator. And this has 3 different waveforms it can make. You can get them in ones that have various complexities. This can do, go ahead and turn it on here, a triangle wave, a square wave, and a sine wave. Let our scope warm up. And we'll talk about this guy next, so don't worry about it too much other than looking at the waveform. But with this, you can adjust. So here we're looking at the frequency. So if I want to make something that looks like the wall power, which is 60 hertz here, you can adjust it down to 60 hertz pretty much exactly. So now I'm making a sine wave, making a square wave, making a triangle wave, and this will sweep through a range of frequencies as well. Put this on channel 1 so it'll trigger and you can see it a little better. So there you can see it's sweeping through a range of frequencies, and you can see it on the frequency display as well. This is really useful if you have some kind of filtering problem, you're trying to figure out what's going on with some high frequency signal that might be getting lost in your circuit. You can inject a signal with this and watch it on the oscilloscope. So these are relatively cheap, a couple $100. But as far as I know, we only have one hanging around in the lab.
We only had one simple one like that.
Yeah.
Yeah, we used to have more complicated one.
But these are really useful to hang on to, and you can do all kinds of things. You can put a DC offset on it, you can change the amplitude, all kinds of good stuff. What we're looking at the waveform on down here is an oscilloscope, which this is one of the most useful pieces of test equipment around, other than a basic volt-ohm meter. And what this is pretty much showing us is a graph of time and voltage. And how it works we could go into, but we don't really have time nor the need. This particular scope has 2 channels, so we can put 2 different input signals in, view them both on the same time base, and then it's got a trigger. So right now I am triggering on this waveform. That's why it's not just bouncing all over the place. If I put it on a channel that's not triggered, you just see like the raw time graph. So it's floating all around on the screen. What the triggering does is it says there is a certain voltage that when I reach that voltage, I'm going to call it time 0. And I'm going to line up all time zeros in one place. So you get this much more stable display that you can look at. Learning how to use an oscilloscope, everyone is totally different. This one is from the, I would say, late 80s or early 90s, where it's in that range where we're transitioning between pure analog scopes and digital scopes. So this has some menus on the screen and things that you can bring up and adjust. It's not necessarily the most intuitive thing in the world, but we're happy to help you figure out how to use it. And it is one of the most frequently used pieces of test gear for looking at signals. If you're having servo problems, or especially if you're having servo problems, you can hook your servo output up to this and see what the pulse width modulation is doing and see in time how things are going. As you'll see in a demonstration that we're going to do a little bit later, you can measure really, really accurately in time and in voltage with this. There's another tool that we don't have in the lab called a logic analyzer. That's sort of like an oscilloscope, except it'll only tell you, is the state of this wire 0 or 1? But they normally have many channels of input, say 16 channels is a common one, and they operate at many megasamples a second. And so if you have some kind of complex digital circuit, you can check the logic at many places in that and make a graph of it over time. So the one I've got connects to my computer, it records all the data, and you can scroll through it and look at it. It's pretty handy. So any questions on the basic equipment that we've got in the lab that you've got access to, or what you would use it for? No? Okay.
So one of the things you want to think about is like how all this stuff is really useful for you for troubleshooting kind of thing, for example, that we did last week. One of the things we don't have, which I wish we had, is a millivolt standard. Just kind of think to yourself, last week we're building this circuit and maybe it doesn't work. You think, well, I wish I could just put 1 millivolt or 10 millivolts into my amplifier and watch what comes out of the other side to test if that's the problem, or if the problem is in my Lisa bridge or somewhere else. And with all these things, you have to think to yourself, okay, like when I'm troubleshooting my circuit, what are the tools that I can use? Voltmeters are pretty useful. That's what we used a lot last week on Thursday, right? You just go back in and just test your circuit at every stage to make sure it looks the way you want it to. And these other things like, like a scope or function generator, they just serve exactly the same purpose for slightly more complicated things. When you're going through your projects, my guess is that in the process of building projects, you're going to run into the same kind of thing. It doesn't work. Why not? Well, who knows? Start from square one, make sure you're sending in things to power. What would happen to this part of the circuit if I put in this signal?
Yeah, so that's really the key, especially in your projects when you're having problems, is to kind of divide and conquer. If you've got your Wheatstone bridge and hooked into your instrumentation amplifier, the first thing you do, thou shalt check voltages. You get the multimeter, check the voltage here, check the voltage here. Is that what you expect? Check the voltage coming out. Does that make sense? What's going into the amplifier? Does that make sense? And what's coming out of the amplifier? You can trace back through this signal chain and find where the broken link is.
And you already have some tools. We don't have a millivolt standard, but you guys know how to build a voltage divider with a potentiometer in it. So you can basically produce any voltage that you want between 0 and 5 and use it as an input into some amplifier or something else. That's a really useful way to think.
Yeah, and there's a really good book called Debugging by Dave Aggins. The library has it. It's thin. You can read it in a couple hours. It goes through a lot of really useful things for debugging, and he tells all these just horror stories of debugging really hard things, like sending video. This is before internet was big, doing video conferencing over phone lines, where you had like 6 phone lines sending data for the single call. And every time, well, sometimes when he got up, the system would freeze and everything locked up, nothing would work, and sometimes it didn't. He finally figured out if he wore a plaid shirt, it was the aliasing of the pattern as he stood up that caused the processor to lock up. So they literally shipped his plaid shirts to the manufacturer of this chip. But I mean, troubleshooting can go crazy. It can drive you insane. Okay, so signal integrity. Keeping signals clean is really hard. This is a graphic I found from the FAA that I thought was a good example of a safety critical application. If you have sensors like DC-DTs or potentiometers that are telling you what the angle of the ailerons on your wings are, and that information is going into the autopilot, it would be really unfortunate if somebody's cell phone call could interfere with that and crash your plane, because people don't turn off their cell phones like they should, right? So that's something where you have to worry about the signal integrity coming from artificial sources like cell phone radio towers, other planes transmitting, natural sources like lightning, and then sources internal to the aircraft, just digital noise from things like computers. One of the old computers that Radio Shack used to sell, the TRS-80, called it the Trash 80, when it was on, if you had an AM radio nearby, you could hear the clock of the computer on the AM radio. So that's obviously a very